Today we'll discuss section 12.2 and continue our study of combinatorics. And I'll begin by reminding you that we've talked about using lists and tables and tree diagrams, and more importantly, we introduced the counting principle as a counting technique. I want to add to that, our toolbox for counting things will continue to grow. Suppose we're arranging a promotional photo shoot for 3 celebrities. And if you like Star Wars, you'll recognize these as Luke, Han, and Yoda. And I'm asking the question, in how many ways can we line them up together for a photo? If you're just going to list them by brute force, one way is to just leave them in the order they appear now. You've got Luke, Han, and Yoda. And then you need to figure out how many ways you can move things around to get a different arrangement. Suppose I decide to keep Luke in the first position and switch Han and Yoda. That would put Yoda in the second position and Han in the third position. Now there's no other arrangement that leaves Luke in the first position, so maybe now I'll slide Luke over into the second position, put Luke in the middle. That means I could put Han on the left of Luke and Yoda on the right, or I could switch that and put Yoda on the left and Han on the right. Now if you think about it, there's no other arrangement that leaves Luke in the middle. So let's move Luke over to the far right. Now let's put Han first, Yoda second, leaving Luke in the third position. The only other thing I can do is switch Han and Yoda. And that's a 6th way to do this. And as you can see, I've put Luke in every possible position, and then I've switched the other 2 around Luke. So there's no other way to do it, and the answer would be 6. You could do this with a tree diagram as well. If you were to break it out that way, you could start off with Luke and branch to either Han and Yoda and so forth. But the point is, either way you do it, there are 6 possible ways of arranging 3 people in line to take a photo. Each of those 6 orderings is called a permutation of those objects. So there are 6 permutations of 3 things taken together. Fortunately, there's a quick way to calculate the number of permutations, and it involves something called a factorial. And the definition involves an exclamation point. Here it says n exclamation point. That's read n factorial, and n factorial is defined to be n times n minus 1 times n minus 2, continuing that pattern to count down to 1. Now, hold that thought. We're going to go off and explore this idea of a factorial, and we'll come back to this spot. So remember this spot, and we'll come back to it. Going back and diverting and talking about factorials, the n exclamation point is read n factorial, and the calculation is simply whatever number is to the left of the exclamation point, you start with that, and then you count down until you get to 1, and you take the product. So 4 factorial is 4 times 3 times 2 times 1, which happens to be 24. 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1, which is 720. 1 factorial, you start at 1 and you count down till you get to 1. Well, you're already at 1, so 1 factorial is just 1. There is one special case that we need that doesn't follow that pattern. As long as n is 1 or 2 or 3 or 4 or any counting number, you can use this formula. But there is a need occasionally for us to define what happens when you get 0 factorial. And it turns out that 0 factorial is by definition equal to 1. I'm not going to talk about why. At this point, it doesn't matter. But in order for our factorials to work the way we want them to work, we have to define 0 factorial to be 1. That's the one that you just have to memorize. It doesn't follow the pattern for the others. Now, you can play with this, but you probably can see just by the definition that factorials can get big really fast. So it's nice to know that your Casio FX260 does have a factorial button. if you look at your calculator, the factorial button is above the number 3 on the calculator. So that means you have to press Shift to get to it. So if I ask you to calculate 8 factorial, you would press 8, then you would do Shift 3. Shift 3 takes you to the factorial. And you don't even have to press equal to, and you'll get 40,320. Now that we know how to calculate factorials, let's go back to the spot I asked you to remember earlier and pick up from there. Remember, we were here just after we had done these permutations of Luke, Han, and Yoda, and found out that there were 6 ways we could line them up for a photo. The important point here, though, I want to emphasize is that it turns out that the number of permutations is actually n factorial, where n is how many distinct objects you have. So here you have 3 people, so it would be 3 factorial. And 3 factorial is 3 times 2 times 1, which is 6. Notice it matches what we got earlier. So rather than having to actually write out every permutation, we can just use the factorial formula and get there very quickly. And again, just for emphasis, that's exactly the same answer we got when we just did it by brute force. Now, you need to remember this. This is a very important result. If you want to count permutations of n distinct objects, all you need to do is calculate n factorial. Occasionally, though, we're interested in counting the number of different arrangements of a group of objects. Now, let's go back to the example that we began with. That's Luke, Han, and Yoda. But what if we added a 4th person? What would that do? What if we added Princess Leia? Well, now that we know that factorials do the counting for us, all we have to do is calculate 4 factorial instead of 3 factorial. Well, 4 factorial is 4 times 3 times 2 times 1, which is 24. So there are 24 different arrangements possible if you've got 4 people. Now, knowing that formula is good enough when the number of objects you're arranging is the same as the number of objects you have to choose from. Because, for example, in the last exercise, we had 4 people and we lined them all 4 up for a photo. But what if you were doing something slightly differently? Suppose we had a bicycle built for 2 and we wanted to pick 2 of those 4 people and put them on the bicycle built for 2. Also keep in mind, if you're looking for the number of ways you could do that, a person sitting on the front seat would be different than that same person sitting on the back seat. So we want to look at the number of arrangements. We're choosing from the 4 celebrities, but we can only take them 2 at a time to get a photo of them on a bicycle built for 2. So this time the count is slightly different. I don't want to take them all 4 at a time. How do you deal with that? Well, let's play with this. I'm going to just randomly reach up and grab 2 of the celebrities. I'll take Luke and Leia. Put Luke on the front seat and Leia on the back seat. So that'd be my first arrangement. Now, you need a strategy to go through every possibility in an organized fashion. So I decided I'm going to leave Leia on the back seat and swap everyone else out. So if Leia stays on the back seat and I take Luke off, I can put Han in Luke's place. That's the second possibility. Again, I want to keep Leia on that back seat as long as possible. So now the only other way to do that is to put Yoda on the front seat. That's a third possibility. At this point, Leia has to come off the back seat or I don't get any more unique arrangements. So I'll take Leia off the back seat and put Luke on the back seat. And then I'll start on the left and I'll pair Luke on the back seat with Leia on the front seat. That's a 4th arrangement. I'm going to leave Luke on the back seat and take everyone else on the front seat. I've already used Leia, so I'll move Leia off and take Han. So now I'm leaving Luke on the back seat. Han goes in the front seat. Again, if I leave Luke where he is and take Han off and put Yoda, that gives me yet a 6th possibility. There's nothing else I can do and leave Luke on the back seat. So I'll take Luke off the back seat now and put Han on the back seat. And I'll start on the left and let Leia be on the front seat. That's a 7th arrangement. Keeping Han on the back seat, now I can put Luke on the front seat. That's an 8th arrangement. Leaving Han on the back seat, I can put Yoda on the front seat. That's a 9th arrangement. Now there's nothing else I can do and still leave Han on the back seat. So I'll bump Han off the back seat and put Yoda on the back seat, and then I'll start on the left again. So Han is off, Yoda goes in the back seat, Leia on the front seat. That's the 10th arrangement. Leaving Yoda on the back seat, now put Luke on the front seat. That's an 11th arrangement. And finally, leaving Yoda on the back seat, I can put Han on the front seat, and that's a 12th arrangement. And there's really nowhere else to go. So there are 12 permutations of 4 objects, and this is important, taken 2 at a time. So I'm still trying to arrange 4 objects, but I'm only taking them in pairs. This is an important distinction because if you're not taking them all, you've got to know how many you are taking at a time, and that's extremely important. So in the previous example, when we took 4 people, we took all 4 at a time. That turned out just to be a factorial. 4 factorial is 24. But when we took them 2 at a time, it turns out to be only 12. We learned if we do take them all, we just use the factorial, as I mentioned. The question is there also a formula if you don't take all of them at once? And the answer turns out to be, lucky for us, yes, there is. And here's what we need. A permutation is an ordering of distinct objects. You often think of them as being in a straight line. If we select R distinct objects from a set of N objects, in other words, you're only taking them R at a time, and arrange them in some order, we call this a permutation of N objects taken R at a time. It's denoted quite often with a capital P and subscripts N on the left and R on the right, or just a capital P and have N comma R in parentheses. Both of those notations are common ways to list a permutation of N objects taken R at a time. And here's the formula. The formula for that is N factorial up top and N minus R factorial down bottom. We're not going to prove this, but we're going to use the result nevertheless. Now let's apply that formula to the bicycle built for 2 problem and see if we get that same answer, which was 12 that we got earlier. So let's plug them in. We had 4 people, so N is 4. We took them 2 at a time, so R is 2. So if you plug in 4 for N and 2 for R, you get 4 factorial over the quantity 4 minus 2 factorial. Well, 4 factorial over 4 minus 2 factorial is 4 factorial over 2 factorial. 4 factorial is 4 times 3 times 2 times 1. 2 factorial is 2 times 1. That's 24 over 2, which is 12. Gives us exactly the same answer we got before. And just like for the factorial, there's a permutation button on your calculator as well. It's above the number 1. That is the permutation button. It's above the 1, so you have to press Shift to access it. So if I wanted to calculate permutation of 4 things taken 2 at a time, here are the keystrokes. Press the 4, do Shift 1, which takes you to the permutation. Then you put in the 2, which is the R, and in order to get that to calculate, you have to press equal. For the factorial, you didn't have to press equal. You just have one number and you hit the factorial shift combination. But when you're plugging in 2 numbers, you have to press equal after the second number to get the calculation to take place. And in this case, you would end up with 12, which again is the same answer we got earlier. So a very important formula. This is the formula for the permutation of N things taken R at a time. Just to practice, if I ask you to evaluate the permutation to 4 things taken 2 at a time times the permutations of 8 things taken 4 at a time, you would calculate the permutations of 4 combination 2 first, which is 4, shift 1, press 2, then you want to hit equal to. Then you do the multiplication symbol. Then you do a permutation of 8 things. So you press 8. Then you do shift 1 again. Then you press 4. And to make it do the calculation, you press equal. And you'll get 20,160. So that's just practice using the calculator. with permutations. There is one more interesting fact that I might mention. In that formula above, if n is equal to r, you would get the permutations of n things taken n at a time. And if you plug that into the formula above, you'll get n factorial over n minus n factorial. Well, n minus n is 0, and 0 factorial is 1, so you get n factorial over 1, which is just n factorial. So if you don't believe it, try on your calculator. If n and r are the same number for a permutation, it's just the same thing as just doing the factorial of that number. You don't have to know that, but it is a nice, interesting fact. Now, suppose we've got 2 of these 4 celebrities, and we're going to choose them as before on the bicycle built for 2, except this time we're not putting them on a bicycle. We're going to give them a star on the Hollywood Walk of Fame. The difference is important. On the bicycle built for 2, the order mattered. Sitting on the front seat was different than sitting on the back seat. But if I'm just choosing 2 people to get a star, it doesn't matter what order I chose them in. It's an important distinction. So for instance, if the 2 chosen were Han and Yoda, it doesn't matter if I do Han Yoda or Yoda Han. In the example on the bicycle built for 2, it did matter. It decided which one was on the front of the bike. But for the stars, it doesn't matter. Problems like that, where the order doesn't matter, has a special name. It's called a combination. Those type problems are combination problems. Now, we've already written out the 12 arrangements for the bicycle built for 2, and we can see that what happens is, with the stars, the order doesn't matter. So we can actually look back at the answer we got for the bicycle built for 2 and just eliminate the duplicates. In other words, if you've got Leia and Han, and you've got Han and Leia, if you're just giving them a star, it doesn't matter what order they were chosen in. So really, 4 is a duplicate of 1, so you can just get rid of 4. And the same thing is true going down the list. If you've got Leia and Han, that's the same as Han and Leia, which is number 7, so you can get rid of the 7. As you keep moving down, number 3 is Leia and Yoda, so you can also get rid of number 10, which is Yoda and Leia, so you don't need that duplicate. Giving them stars, the order doesn't matter. And as you move down the list, you've got Luke and Han, and then number 8 is Han and Luke, so you can get rid of number 8. Number 6 is Luke and Yoda, and number 11 is Yoda and Luke, so you can get rid of that number 11. It's a duplicate. And then finally, you've got Han and Yoda, and number 12 is Yoda and Han, so you can get rid of number 12. And that leaves you simply with 6, where you're just giving them a star. The order doesn't matter. Is there a formula for that? Yes, there is. It has to do with the combination. A combination is a subset of a set of distinct objects where order is not important. If we select R objects from a set of N objects without regard to order, we call this a combination of N objects taken R at a time, and it's often written exactly as for a permutation, except we use capital C instead of capital P. So we can put the capital C there with the subscript of N on the left and R on the right, or we can write capital C with N comma R in parentheses. So the capital P for permutation changes to capital C for combination. And there's your formula. Combination of N things taken R at a time is N factorial in the numerator, and in the denominator is the product of R factorial and N minus R factorial. That's the formula when order doesn't matter. If we apply that to that Hollywood Walk of Fame star problem, remember we got an answer of 6 when we did it by brute force. Let's see if we can get the same answer by plugging in. In this problem, we had 4 people taken 2 at a time where order doesn't matter, so it's a combination. Plugging into that formula for a combination, we get 4 factorial over the product of 2 factorial and 4 minus 2 factorial. Well, that's 4 factorial over 2 factorial times 2 factorial. 4 factorial is 4 times 3 times 2 times 1, and 2 factorial is 2 times 1. If you write all that out, 4 times 3 times 2 times 1 is 24, and 2 times 1 times 2 times 1 is 4, and 24 divided by 4, big surprise, is 6. It's exactly the same answer as when we did it by brute force. So these formulas allow you to get to the count much faster than having to do it by brute force. And again, you won't be surprised to know that there's a button on your calculator for that. It's above the number 2. And you have to press the shift key to access it. So if I were to calculate the combination of 4 things taken 2 at a time, I would press 4, then I'd do shift 2, then I would press 2, which is the R, and to calculate it, you hit equal to, and you'll come up with the number 6. Again, it's the same answer we got before. Now, one of the things you'll come across when you're doing these is that when you read a problem, sometimes you have to figure out, is it a permutation or is it a combination? For example, suppose there are 10 different books in a box and 4 of them are to be arranged on a shelf. How many different arrangements are possible? You're taking 10 books and you're going to take 4 of them and arrange them on a shelf. Well, if you're arranging them on a shelf, by definition, order matters. So that makes it makes it a permutation because order matters. If you get that wrong, of course your answer will be wrong. You have to know here that order matters. You're making arrangements. By definition, that's order. So I use the permutation formula, plugging 10 in for N and 4 in for R. 10 books, 4 at a time. So that's 10 factorial over 6 factorial. And if you do the calculation, that comes out to be 5,040. There are 5,040 different arrangements of 10 books taking 4 at a time on a bookshelf. You could also do this problem, just FYI, by using the counting principle directly. You could think of it as a 4-stage experiment where you're choosing book number 1, book number 2, book number 3, and book number 4. And if you think about it, you have 10 books. So for your first stage of the experiment, you can choose any of the 10. But once that first book has been chosen, you only have 9 left to choose for the second position, and 8 for the third position, and 7 for the fourth position. And 10 times 9 times 8 times 7, believe it or not, is also 5,040. So you could actually do that problem by the counting principle, and you'll find that to be true quite a lot. The counting principle is kind of a bedrock principle, and sometimes you can use it in place of using one of these other formulas if you really want to. But it is the same answer either way you do it. If you want to do that on your calculator, you type in 10, hit shift 1, which is the permutation combination, then you'd press 4, and that would give you 5,040. Let's do another example. Suppose we've got that 10 different books again, but this time Jan wants to choose 4 of them to read while going on some trip. Maybe she's taking them into the car with her. How many different arrangements are possible? Now, how is that different from putting books on a bookshelf? Well, if you're putting books on a bookshelf, you're arranging the books in different order. Here, Jan doesn't care which book is chosen first. She is simply going to grab 4 books and bring them with her on the trip. Order doesn't matter at all. The order she picks those books is totally irrelevant to Jan. That means it's a combination. Again, if you get that wrong, you're going to get the answer wrong. It's a combination because order does not matter. Once you figure that out, you use the combination formula, again plugging 10 in for N and 4 in for R, and you end up with 10 factorial over the product of 4 factorial and 6 factorial, and that comes out to be 210. And again, if you wanted to do that calculation with your calculator, 10 factorial over 6 factorial. And if you want to do that calculation in your calculator, you type in 10, hit shift 2, which gives you the combination, and then you do 4 and equal to, and that gives you the same answer. So even though I'm giving you the formulas for combinations and permutations, really you just need to know how to do it on the calculator, and you can avoid having to plug into these formulas. So I'm doing it sort of just to reinforce that these formulas really do give you the right result, but I'm also pointing out that the calculator is the fastest and best way to do it. Sometimes a problem requires the use of more than one counting tool. So in order to discuss problems like that, it's probably a good time to go back and remind ourselves of all the tools we've developed so far. Remember, we talked about lists, tables, and tree diagrams. We talked about the counting principle. We talked about the permutation formula as a factorial. Remember, a factorial is a special type of permutation where you take them all at a time. We've talked about permutations when you don't take them all at a time. You take n objects r at a time. We've talked about combinations where order doesn't matter. So we're building a toolbox of tools that help us count arrangements of things and different items that we want to count. Let's look at a particular example. Suppose a committee of 4 people is chosen from 8 women and 8 men. How many different committees are possible consisting of 2 women and 2 men? Well, here, order isn't important on the committee. You pick 2 people to be on a committee, or 4 people, or 8 people, but what order you put them on the committee is totally irrelevant. So we're going to use combinations to count this. But there's really 2 different stages. One stage is to choose the women, and the other stage is to choose the men. So even though for choosing women, we know order doesn't matter, we'll use combinations. And for choosing men, the order doesn't matter, so we'll use combinations. But since it's a 2-stage experiment, it will be embedded inside the counting principle. In other words, the first stage of the process is the number of ways to choose the 2 women. The second stage of the process is the number of ways to choose the men. And when we find those 2 quantities, we multiply them together by the counting principle, and that gives us the total arrangements. So, because the women being chosen is a combination, again, because order doesn't matter, we use the combination formula. There are 8 women, and we want to choose 2. So that's 8 women chosen 2 at a time, and it's a combination because order doesn't matter. Then if you go to the men, there are also 8 men. It doesn't have to be the same, but in this case, there are also 8 men, and you're also choosing 2 men. So that'd be the combination of 8 men taken 2 at a time, and the product of those 2 calculations give you the total. So now we've got to calculate the combination of 8 things taken 2 at a time. Well, that is 8, shift 2 for combination, press 2 because that's the R, and hit equal to, and that gives you 28. And just by happenstance, notice that the other combination is also a combination of 8 things taken 2 at a time. So it turns out that that's also going to be 28. Doesn't have to be the same, but in this case it is. So there are a total of 28 times 28, which is 784 different ways you can choose 2 women and 2 men to be on a committee if there are 8 women and 8 men to start with. And notice that the combination calculation was used for each stage in the counting principle, which had 2 stages. Choosing the women was the first stage, choosing the men was the second stage. That's an important point to remember. This is a process, this is an example where you actually have two of your tools going on at the same time. You're using the combination formula, but you're also embedding that inside of the counting principle. If 5 cards are randomly chosen from a standard deck of cards, how many hands contain 4 queens? Now you've got 5 cards, and I told you that you had to have 4 queens. So even though they didn't come right out and say it, by implication, there's got to be another card that's not a queen as chosen as the 5th card. You sort of have to read between the lines there. You're choosing 5 cards. They told you what 4 of them have to be. So there's still a 5th card involved. So you're still choosing 5 cards. They just told you what they wanted 4 of them to be. But the basic thing here is order isn't important. So we can use combinations to count this. We don't care what order we draw these cards in. We're just going to put them into our hand, and they're going to be in our hand. It doesn't matter what order we drew them. So it's a combination. But like the previous problem, it really involves 2 subtasks. There are 2 stages to this experiment. One stage is choosing the 4 queens, and the other stage is choosing the one that wasn't a queen, the 5th card. So if you think about queens versus non-queens, every standard deck has 4 queens. That means 52 minus 4. That means 48 cards are not queens. So I'm thinking the deck is being partitioned into queens and not queens. There are 4 queens in the deck, which means the other 48 cards are non-queens. So embedding this in the counting principle, I want to choose my queens first. So the first stage of the process is the number of ways to choose the 4 queens. Once I've chosen the 4 queens, then I want to choose one of the other cards. There are only 4 queens in the deck, so the other card has to be something other than a queen. So since it's a combination, if I'm choosing queens, there are only 4 queens in the deck, and I want to choose 4 queens, so that's a combination of 4 queens taken 4 at a time. For the non-queens, again, order doesn't matter, but this time there are 48 non-queens, and I only want to choose one of them, so that's a combination of 48 things taken 1 at a time. Now, if you do the calculation for a combination of 4 things taken 4 at a time, that's 4, shift 2, and then R is also 4, and you hit equal to, and it comes out to be 1. If you do combination of 48 things taken 1 at a time, you type in 48, do shift 2, then you press 1, which is the R, and you press equal to, and you end up with 48, and 1 times 48 is 48. Again, another problem where you're using 2 of your tools. You're using the combination tool inside of the counting principle tool. If 5 cards are randomly chosen from a standard deck of cards, how many hands contain exactly 2 2s and 2 8s? It's very similar to the other problem, and again, for the same reason as was true for the other problem, order doesn't matter, so these are going to be combinations. And also, like the last problem, it's actually going to be a counting principle problem at the base, but this time there are 3 subtasks, or there are 3 stages. This is a 3-stage experiment. The first stage, you're going to choose your 2s. Second stage, you're going to choose your 8s, and if you're going to choose 2 2s and 2 8s, and there are 5 cards, that means you've also got to choose a 5th card. So think about this. You're going to take the number of ways to choose your 2s, your 2 2s. You're going to find the number of ways to choose your 2 8s, and then you're going to find the number of ways to choose your one more card. That makes the 5th card that can't be a 2 or an 8, because we only want exactly 2 2s and exactly 2 8s. So if that 3rd card were either a 2 or an 8, we would have more than 2 2s or more than 2 8s. So going back, choosing your 2s is a combination because order doesn't matter. There are 4 2s in the deck, and we want to choose 2 of them. So that's a combination of 4 things taken 2 at a time. Then we want to move to the 8s. Again, there are 4 8s in the deck, and we want to choose 2 of them. So that's also a combination of 4 things taken 2 at a time. Now the last one, think about it. You want it to not be an 8, not be a 2. Well, there are 4 2s and there are 4 8s. So for that 5th card, order still doesn't matter, but there are only 44 of them, because 52 minus 4, take away the 4 2s and the 4 8s, leave only 44 cards. So that last card has to come from the 44 cards that aren't 2s or 8s. And when you do the calculation, the combination of 4 things taken 2 at a time is 4, shift 2, 2 equals, and that comes out to be 6. Well, that actually, for the 8s, it comes out to be exactly the same. 4, shift 2, 2 equals. That's also 6 because it was exactly the same combination. And then finally, combination of 44 things taken 1 at a time. That's 44, shift 2, 1 equals, and that comes out to be 44. And then by the counting principle, you multiply those numbers together, 6 times 6 times 44, and you end up with 1,584. So if you choose 5 cards randomly from a standard deck of cards, there are 1,584 different hands that contain exactly 2 2s and 2 8s. How about this one? Lucy was born on 12/11/1989. How many 8-digit codes could she make using the digits in her birthday? Well, the thing to do is just write out those digits. You've got 4 1s, you've got a 2, and you've got an 8, and you've got 2 9s. So those are the 8 digits that you're supposed to be using, and we want to know how many 8-digit codes can you make using those 8 digits. This is a little different than anything we've done before, because when we were doing things before, when we were putting things in order, the things were different. Like there were different books or different people, but this time all 4 of those 1s are really the same, and then those 2 9s are the same. So we need a different formula. I'm not going to derive it, but I am going to show you what it is and how to use it. And here's the trick. The number of distinguishable permutations of n objects where k sub 1 are identical, k sub 2 are identical, etc. is given by the formula n factorial over the product of k sub 1 factorial, k sub 2 factorial, etc. In other words, you take n factorial, that's the number of digits in this case, but you divide by the number of duplicates, factorial. So up top, n is how many, in this case, digits there are. There are 8 of them. So that goes up top. Then you look at repetitions. There are 4 1s, so that's what k sub 1 is. There's only 1 2, so k sub 2 is 1. There's only 1 of those. K sub 3, which is the 8, there's only 1 of those. And there are 2 9s, so k sub 4 is 2. Using that result, the number of 8-digit codes is 8 factorial over the product of the k factorials. That'd be 4 factorial, 1 factorial, 1 factorial, 2 factorial. Well, 4 factorial is 24. We've done it before, but you can punch it out on the calculator. 1 factorial is 1, and 2 factorial is 2 times 1, which is 2. So you get 8 factorial over 24 times 1 times 1 times 2, which is 48. And if you finish out the calculation, you'll find out that there are 840. So there are 840 different 8-digit codes that you could make using the digits in Lucy's birthday. And again, that's a variation on anything we've done before, and the reason you need it is because those digits are not all distinct. If those were 8 different digits, it would just be 8 factorial. But because some of the digits are duplicates, you have to divide the factorial by the factorial of the duplicate counts. 6 identical coins are tossed. How many possible arrangements of the coins include 3 heads and 3 tails? Now, if you think of this problem in terms of what we just did, this is easy. If I'm thinking of heads and tails, just think of the head as being capital H and tails as being capital T, and think about writing a 6-letter word. You want it to get 3 heads and 3 tails, so it's like writing H, 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 T, 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 and you want to know how many different ways there are to arrange 3 H's and 3 T's. Well, that's like a 6-letter word where you have duplicates in the H's and duplicates in the T's, and the formula we just used and learned a minute ago applies here. You've got 6 objects, but they're not distinct. So you're going to use this formula where you've got some things that are not identical and are identical. So you take n factorial, that's the number, that's just the raw count. 3 H's, 3 T's, 3 plus 3 is 6. And then you look at the duplicates. There are 3 H's, so k sub 1 is 3. There are 3 T's, so k sub 2 is 3. So the result is 6 factorial over the product of 3 factorial and 3 factorial. And if you do the calculation, you'll see that it comes out to be 20. So the trick to this problem is thinking of heads and tails as letters. H for heads, T for tails, and then it becomes just like the problem we did before where you have letters instead of numbers, but you have duplicate letters instead of duplicate numbers. But the principle is the same. Along the way, I've been building up our toolbox. I want to go through this one more time. We started off with the lists and tables and tree diagrams. Then we moved to the counting principle. Then we talked about n factorial, which is a special permutation where you take everything all at once, like n things n at a time. Then you have the permutation where you have n objects, but you're only taking them r at a time. Then you move to the combinations where you're taking n objects r at a time, but order doesn't matter. And now we've thrown in this formula about distinguishable permutations of n objects where you have some identicals. And that's where we stand with our toolbox for doing these type problems.